They are smaller than a city, yet heavier than our Sun neutron stars, the most extreme objects in the universe. Born from the death of giants, they crush matter, twist light, and bend time itself. Tonight we'll explore their quiet power and impossible physics. If you enjoy the journey, please like, subscribe, and share, and tell us in the comments, what do you find most fascinating about these cosmic monsters? Thank you for watching. Now, let's begin. Across the vastness of the universe, stars are born from immense clouds of hydrogen and helium that drift through galaxies. Gravity gathers this gas into clusters, drawing the particles closer until density and temperature rise to a critical point. In this deep interior, atoms fuse, releasing radiant energy that pushes outward against the inward pull of gravity. For millions or even billions of years, this balance holds steady, shaping every form of starlight visible in the night sky. Stars vary in mass, brightness, and temperature, but all are bound by this same equilibrium, an inward collapse prevented by the outward pressure of fusion. The lives of these stars are cycles of burning expansion and transformation, and their endings depend on how massive they are when the fuel begins to run out. In smaller stars like the Sun, hydrogen fusion gives way gradually to helium fusion. The outer layers expand into a red giant while the core contracts. Eventually, the outer envelope drifts away as a planetary nebula, leaving a dense remnant called a white dwarf. Its mass is roughly that of the Sun, but compressed into the size of Earth. Electrons resist further collapse through what is called degeneracy pressure, and the faint glow fades slowly over billions of years. This is a quiet and stable death. But for massive stars, the process is far more violent. When a star contains many times the mass of the Sun, the core becomes too heavy for even the most intense fusion reactions to support it. As nuclear fuel depletes, gravity begins to dominate. The internal pressure drops, and the balance that has held for so long collapses. Within moments, the core compresses at extraordinary speed. In the collapsing heart, densities climb far beyond those of ordinary matter. Protons and electrons merge into neutrons through a process called inverse beta decay, releasing neutrinos that stream outward in enormous numbers. The star's outer layers, no longer supported, fall inward, bounce off the dense core, and rebound in a colossal explosion known as a supernova. For a brief time, the dying star shines brighter than an entire galaxy, scattering heavy elements into surrounding space. After this explosion, what remains depends on the mass of the original star's core. If it is below about 3 times the mass of the Sun, gravity compresses the matter into a neutron star, a sphere only about 20 kilometers across, yet containing more mass than the Sun. If the core is heavier still, the collapse continues past the point of no return, forming a black hole from which not even light can escape. Between these two extremes lies one of nature's most extraordinary objects, the neutron star, where atomic nuclei are crushed together so tightly that a single teaspoon of its material would weigh billions of tons. This is the boundary between known matter and the unknown. The discovery of neutron stars transformed astrophysics in the 20th century. When the first pulsar, a rapidly spinning neutron star emitting regular bursts of radio waves, was detected in 1967, it revealed that these remnants were not just theoretical curiosities, but real celestial objects common across the galaxy. Over time, observations in X-rays, gamma rays, and visible light revealed their diversity. Some rotate hundreds of times per second. Others possess magnetic fields trillions of times stronger than Earth's. They are the most compact, dense, and magnetic bodies known that can still be directly observed. The formation of a neutron star is an act of gravitational alchemy. During collapse, the energy released in neutrinos briefly outshines the visible universe. This torrent carries away about 99% of the supernova's energy, allowing the remainder of the star to explode outward. The core, stripped of most of its heat, stabilizes as neutrons arrange into a dense lattice or superfluid mixture depending on internal temperature and pressure. What emerges is neither ordinary matter nor a simple extension of it, but something entirely new matter, compressed to the limits allowed by physics. Around the newborn neutron star, expanding shells of gas and dust form a nebula glowing with the energy of the explosion. These remnants, such as the Crab Nebula, become laboratories for studying extreme physics. As the material cools, the neutron star's rotation slows, gradually releasing stored rotational energy through magnetic fields and radiation. In some cases, the object remains hidden behind the debris for centuries before becoming visible again. In others, its pulses or bursts reach Earth almost immediately, providing clues to its interior structure. The processes leading to these ends are part of the universe's continuous recycling of matter. Hydrogen forged in the Big Bang becomes helium in stellar cores, then heavier elements in later fusion stages or during explosive deaths. Iron, nickel, and many of the elements essential for planets and life are created in such catastrophic events. Each generation of stars enriches the interstellar medium from which the next generation will form. Thus, even the most violent deaths contribute to future creation. In this balance between stability and collapse lies a delicate law of cosmic evolution. Stars, more massive than about 8 times the Sun's mass, cannot end as white dwarfs. Their gravity is too strong. The immense pressure in their cores pushes matter to states that defy normal atomic behavior. When fusion stops, no known force can resist the collapse until neutron degeneracy pressure. The quantum mechanical resistance of neutrons being squeezed together halts it. This produces the neutron star, an object only a few tens of kilometers wide, but with a gravitational field so strong that time itself slows near its surface. The physics governing this process is well understood in its broad strokes, but still incomplete in its details. The behavior of matter at such densities cannot be reproduced in any laboratory on Earth. Even the most advanced particle accelerators fall short of reaching the pressures found in a neutron star's core. Instead, scientists infer their properties through observation, measuring their masses, radii, and spin rates, studying their emissions, and tracking gravitational waves when they collide. These data allow the refinement of models describing what happens inside. In the quiet sky, each neutron star is a marker of a life that once burned brightly and died violently. They remind us that the universe's most powerful transformations occur not in chaos, but in balance, the balance between creation and destruction, energy and gravity, stability and collapse. The calm persistence of their radiation pulsing across millions of years is a steady rhythm against the background of cosmic silence. This is where the story begins, in the end of ordinary stars and the beginning of something far denser, smaller and stranger, where matter itself becomes almost pure gravity held just short of the abyss. At the end of a massive star's life, gravity no longer has an opposing force strong enough to hold it back. For millions of years, fusion within the core has converted lighter elements into heavier ones, releasing the energy that balances the star's enormous gravitational pull. But when the core accumulates, iron fusion stops yielding energy. Iron nuclei cannot fuse further without consuming energy instead of producing it. The delicate equilibrium that has sustained the star collapses in a matter of seconds. The immense gravitational field, once balanced by thermal pressure, now becomes an unstoppable inward force. Deep within the core, matter falls inward at nearly a quarter the speed of light. The atoms themselves cannot survive the compression. Electrons are forced into protons, forming neutrons and neutrinos. This transformation releases a flood of these ghostly particles, trillions upon trillions per cubic centimeter, streaming through the collapsing star at almost the speed of light. They carry away energy, leaving the core denser with every passing millisecond. What had been the size of Earth now shrinks to a sphere only a few tens of kilometers across. As the collapse accelerates, the infalling material overshoots the new equilibrium point. The outer layers slam into the core, producing a shock wave. For a moment, this shock stalls, unable to break through the dense matter ahead. But the neutrinos escaping from the core deposit enough energy to revive the shock, propelling it outward through the star's envelope. This resurgence is the birth of the supernova explosion. In less than a second, the outer layers are blown away into interstellar space, while the core remains behind as a neutron star. The energy of the explosion briefly rivals that of all the stars in the galaxy combined. For observers, this process unfolds invisibly until the blast reaches the surface. When it does, the brightness can increase by a factor of billions. To distant civilizations, it would appear as a sudden new point of light in the sky. In historical times, such explosions have been recorded as guest stars visible even in daylight. The mechanism behind them, however, remained a mystery until the physics of collapse was understood. The moment gravity wins, the star ceases to be a source of fusion and becomes an engine of compression. The structure of the collapsing core is extraordinary. As density rises beyond the capacity of atomic nuclei, ordinary matter transitions into a fluid of nucleons. The quantum mechanical effects that dominate on microscopic scales begin to govern macroscopic behavior. The neutrons obey the Pauli exclusion principle, which prevents them from occupying the same state. This resistance becomes the final barrier that halts total collapse. The resulting object neutron star is the smallest and densest stable configuration allowed by nature. It represents the last stand of matter before the event horizon of a black hole. Around this remnant, the expelled layers of the star form a rapidly expanding shell of hot gas. The interaction between the blast wave and the interstellar medium produces X-rays and visible filaments that persist for thousands of years. This debris becomes a cradle for new stars and planets in the distant future, seeding the cosmos with elements heavier than iron. Within this aftermath, the newborn neutron star cools and stabilizes. For the first few minutes, its surface temperature exceeds 1 billion degrees. It emits intense bursts of neutrinos that escape freely now that the surrounding material has thinned. Gradually, radiation becomes the primary means of energy loss, and the neutron star begins its long cooling journey through cosmic time. At this stage, the magnetic field becomes significant. The progenitor star's magnetic field is amplified by the collapse-conserving magnetic flux as the radius shrinks. The field can grow to unimaginable strength, trillions of times that of Earth. Such an intense field channels particles and radiation, shaping the emerging magnetosphere. If the remnant rotates rapidly, which most do the combination of rotation and magnetism, will power beams of electromagnetic radiation that sweep through space like cosmic lighthouses. These will later be observed as pulsars, but for now the newborn neutron star is still hidden within the shroud of its own supernova remnant, unseen and cooling. The energy scales involve DeFi comprehension. The collapse converts roughly 10% of the star's mass into energy mainly carried by neutrinos. Yet only a small fraction of this output drives the explosion. The rest escapes into the cosmos, carrying with it clues about the inner physics of the event. During a nearby supernova, detectors on Earth can register these fleeting particles, confirming the invisible processes that occur when gravity overwhelms all other forces. The detection of neutrinos from supernova 1987. A provided direct evidence of this mechanism, marking the first time humanity had witnessed the invisible collapse of a star through its ghostly messengers. From a physical standpoint, the core collapse supernova is a moment of perfect efficiency. Gravity gathers, accelerates, and compresses, converting potential energy into kinetic, then into radiation and neutrinos, leaving behind the densest object short of a black hole. The newly formed neutron star spins rapidly because the collapse conserves angular momentum. A star that once rotated once every few days may now rotate dozens or hundreds of times each second. Over time, the rotation will slow, but the initial period defines the magnetic and energetic behavior of the object for millions of years. If the mass of the core exceeds a certain threshold, neutron degeneracy pressure fails to stop the collapse. The remnant then becomes a black hole. This division line between neutron star and black hole is narrow but profound. It defines the boundary between observable and unobservable matter. In neutron stars, light still escapes. In black holes, it does not. The difference is not one of nature, but of degree gravity pushing one step further beyond the limits of matter. The victory of gravity in the final moments of a massive star's life reshapes the cosmos. Every neutron star is a relic of that collapse, a permanent reminder of gravity's supremacy over thermal energy radiation, and even the atomic structure of matter. Yet this victory is not absolute. It creates something new. The neutron star endures small and incredibly dense holding together through the counterpressure of quantum forces. Its formation marks both an ending and a beginning, the end of nuclear fusion, the beginning of a new phase of matter. Around the galaxy, millions of such remnants drift silently. Many no longer visible to telescopes, their radiation faded beyond detection. Yet their presence can be felt indirectly through the motion of companion stars or the faint glow of old supernova remnants. Each one was born from the moment when gravity triumphed a brief catastrophic compression that converted a living star into an object where matter is reduced to its simplest form. In that instant, nature demonstrates both its violence and its precision, its capacity to destroy and to preserve all within the same event. In the seconds following the collapse of a massive star's core, a new kind of object takes shape. The chaotic forces that have torn the star apart leave behind a remnant compressed to densities far beyond imagination. Inside this sphere, only about 20 kilometers across, the remnants of protons and electrons have merged into neutrons, forming a solid core where atomic structure no longer exists. This is the birth of a neutron star, an event of staggering violence and equally profound transformation. In this brief moment, the universe forges one of its most extreme creations, a boundary between matter as we know it and matter transformed by pressure and gravity into near pure density. The newborn star begins its life amid a storm of radiation, neutrinos, and magnetic energy. Immediately after the explosion, the core's temperature is measured in billions of degrees. For roughly 1 minute, it glows with the heat of 10,000 suns condensed into a space the size of a city. Neutrinos continue to stream from the interior, cooling the matter and carrying away energy with incredible efficiency. The outer layers of the progenitor star, blown apart by the supernova shockwave, expand outward at thousands of kilometers per second. For days and weeks, the light from this explosion dominates the surrounding region of space, while deep within the fading glow, the neutron star stabilizes. Its gravitational pull is immense, roughly 200 billion times stronger than that of Earth, yet it holds its form in perfect balance through quantum mechanical pressure. The newly formed crust begins to crystallize as temperatures fall below 1 billion degrees, creating a surface denser than any solid found elsewhere in nature. As it cools, the star's rotation asserts itself. Conservation of angular momentum, the same principle that makes a spinning skater turn faster when pulling in their arms, drives the neutron star to rotate hundreds of times per second. Some of these remnants reach spin rates so high that their equators move at nearly a fifth the speed of light. The rotation is not smooth. The immense gravitational field distorts the star's shape slightly, and the magnetic field amplified by the collapse to astonishing intensity extends far into space, creating a magnetosphere filled with charged particles. Within moments of its formation, the neutron star becomes an engine of radiation. The first phase of a neutron star's life is marked by cooling and stabilization. The emission of neutrinos dominates the energy loss for about 100 seconds, after which photon radiation takes over. The surface emits high-energy X-rays, gradually fading as the temperature decreases. The star's magnetic field, twisted and compressed by the collapse, can reach up to a quadrillion times the strength of Earth's magnetic field. This immense field channels particles along its lines, accelerating them to relativistic speeds and producing beams of electromagnetic radiation. When these beams intersect, Earth astronomers detect them as pulses, a phenomenon that would later define pulsars. But in these first moments, the newborn neutron star is surrounded by a thick shroud of expanding debris, invisible except through neutrinos and high-energy photons that manage to escape. Within minutes, the structure of the neutron star settles into distinct layers. At the surface lies a thin atmosphere of ionized atoms no thicker than a few centimeters, radiating thermal light. Beneath it, the outer crust forms consisting of nuclei packed into a crystalline lattice bathed in a sea of electrons. The deeper layers grow progressively denser until atomic nuclei dissolve and the matter transitions into a sea of neutrons and protons. The entire object is a monument to pressure, an experiment in what happens when gravity tests the limits of physics. Over the next few hours, the neutron star begins to interact with its surroundings. The expanding shock wave drives matter into the interstellar medium, creating a nebula of glowing gas. The newly born star's magnetic field traps some of the surrounding plasma, generating bursts of radio and X-ray emission. In some cases, the neutron star remains bound to its companion if it was part of a binary system before the supernova. In others, the explosion imparts a violent kick, hurling the remnant through space at hundreds of kilometers per second. Many neutron stars now race through the galaxy as invisible travelers carrying the story of their violent creation within their dense interiors. Inside, the density is beyond comparison. 1 cubic centimeter of neutron star matter weighs hundreds of millions of tons. The particles are squeezed so closely together that they behave collectively, forming a quantum fluid. The outer crust remains solid, but below it the neutrons become superfluid, flowing without resistance. Protons within these layers form a superconducting medium, allowing magnetic fields to move in quantized tubes through the interior. These strange states of matter impossible on Earth define the neutron star's long-term evolution. The balance between rotation, magnetic field, and cooling determines how it will appear across cosmic time, whether as a quiet cooling remnant or as a powerful pulsar emitting radiation across the galaxy. As the surrounding supernova remnant expands, its light begins to fade. Within months, the neutron star becomes the primary source of energy in the system. Observers would see a central X-ray source surrounded by filaments of glowing gas, much like the Crab Nebula, which houses one of the most famous pulsars known. The pulse of energy from this central object is a sign of continuing transformation, rotational energy slowly draining away into space through electromagnetic radiation and particle winds. The star's surface continues to cool, but deep inside the density and pressure remain stable. The neutrons have reached their equilibrium, neither collapsing further nor expanding outward. The object is now as permanent as anything in the cosmos can be. The birth of a neutron star is not only the end of a single stellar life, It is part of the broader cycle of matter in the universe. The explosion disperses carbon, oxygen, calcium, and iron elements formed in the star's core into interstellar clouds that will later condense into new stars and planets. The neutron star left behind is a relic of this process, an enduring reminder of gravity's capacity to compress and preserve. Over millions of years it will spin more slowly, its light fading into darkness, but it will not dissolve or decay. Its surface will become cooler than any visible star, yet its interior will remain dense and strange, sustained by the laws of quantum mechanics. Even now, as astronomers detect young neutron stars in nearby galaxies, each one tells the same story: a moment when gravity overcame energy, when matter crossed the boundary between atoms and pure compression. These remnants are fossils of collapse, their very existence a record of cosmic balance. From the chaos of destruction, a new stability emerges, an equilibrium not of fusion but of degeneracy, where the smallest particles hold back the greatest of forces. This moment of birth defines the rest of a neutron star's long and silent life. It begins amid light and violence, yet continues in stillness, carrying within it the memory of the moment when gravity and quantum mechanics met and found peace in compression. Across the Milky Way, hundreds of millions of stars have already lived and died, leaving behind compact remnants scattered through its spiral arms. Among these relics, neutron stars form a hidden population, each one the result of a catastrophic collapse that ended a once luminous stellar life. They do not shine like ordinary stars. Most are faint, invisible in optical light, detectable only through the high-energy radiation that escapes from their hot surfaces or magnetic poles. Yet they are everywhere, drifting through the galactic plane, orbiting companions, or racing through space after the asymmetric blast that hurled them free from their birthplaces. The galaxy is a graveyard of stellar cores, and neutron stars are among its most enduring occupants. Astronomers estimate that one forms somewhere in the observable universe every few seconds. Each supernova explosion adds another to the population, though most remain unseen. Only when their magnetic and rotational properties align to emit detectable radiation do they reveal themselves as pulsars or magnetars. These are the visible tip of a much larger unseen structure. Many neutron stars emit nothing at all, their magnetic axes misaligned or their radiation too weak to reach Earth. They travel silently dark against the background of space, detectable only through their gravitational influence or occasional interactions with nearby matter. Within our own galaxy, the known neutron stars number in the thousands, but calculations suggest there should be hundreds of millions. Most are solitary, drifting through the interstellar medium on trajectories inherited from their violent births. The kick imparted by an asymmetric supernova can send a neutron star moving at hundreds of kilometers per second, fast enough to escape its parent cluster and travel into the galactic halo. Some wander far above and below the Milky Way's disk, carrying their magnetic fields and rotation through deep space. These lonely travelers cool over millions of years, fading beyond detection, yet persisting indefinitely as frozen monuments of gravitational victory. Others remain in binary systems orbiting ordinary stars or other compact remnants. These pairings are astrophysical laboratories, where the behavior of extreme matter and gravity can be observed directly. In some cases, the neutron star accretes material from its companion, drawing it into an accretion disk that heats to millions of degrees and emits powerful X-rays. Such systems are known as X-ray binaries, and they exhibit remarkable variability as magnetic fields funnel matter onto the neutron star's surface. The impact of infalling material releases bursts of energy, sometimes periodic, sometimes chaotic as the magnetic poles channel the flow. These interactions can spin the neutron star up to astonishing speeds, creating millisecond pulsars that rotate hundreds of times per second. The distribution of neutron stars across the galaxy follows the pattern of star formation. Most lie within the thin disk where massive stars are born near the spiral arms rich in gas and dust. They mark the sites of ancient explosions, sometimes still surrounded by faint remnants of expanding gas. The Crab Nebula, for instance, is the residue of a supernova witnessed nearly 1,000 years ago, its central pulsar still spinning 30 times each second. Such remnants illuminate the life cycle of stars' massive birth, brilliant death, and lingering afterglow. Observing them allows astronomers to trace the chemical and dynamical evolution of the galaxy itself. Over cosmic time, neutron stars accumulate in diverse environments. Some remain embedded in star-forming regions, others drift into interstellar voids. In globular clusters, ancient spherical collections of stars orbiting the galactic halo densities are high enough that close encounters between stars are common. The neutron stars can capture companions through gravitational interactions, forming exotic binaries and even triple systems. These old clusters serve as repositories for relics formed billions of years ago, their neutron stars still active after ages far longer than human history. In contrast, in the galactic plane where new stars continue to form, young neutron stars are still being created, often within a few thousand light-years of their parent molecular clouds. Outside the Milky Way, other galaxies harbour their own populations of remnants. Observations of nearby galaxies such as the Large Magellanic Cloud reveal young pulsars born in recent supernovae. Even in distant galaxies billions of light-years away, the signatures of neutron stars can occasionally be detected through high-energy flares or short bursts of gamma rays. These events remind astronomers that the life and death of stars follow the same physical laws everywhere, repeating endlessly across space and time. The presence of so many neutron stars has subtle effects on the galaxy's evolution. Though tiny in size, they contribute significantly to its gravitational mass. Their combined gravity influences the motion of nearby stars and gas clouds, shaping the dynamic balance of the galactic disk. When two neutron stars in a binary system merge, they release gravitational waves that ripple through space-time and eject heavy elements into their surroundings. Over billions of years, such mergers enrich the galaxy with gold, platinum, and other rare materials. Each collision adds a small but measurable amount of these elements to the interstellar medium, linking the quiet abundance of metals in planets and asteroids to the violent deaths of ancient stars. In the quiet between these cataclysms, most neutron stars continue their solitary journeys. Their surfaces cool from billions to millions of degrees, eventually radiating primarily in infrared and radio wavelengths. Without a companion or strong magnetic field, they fade into obscurity, effectively invisible. Yet their interiors remain unchanged. Even after 100 million years, the density and structure of a neutron star remains stable, supported by degeneracy pressure that no natural process can overcome short of another catastrophic event. The universe's oldest neutron stars are likely as dense and compact now as the day they formed. For astronomers, detecting and studying these objects requires ingenuity. Radio telescopes pick up pulses from spinning neutron stars, while X-ray observatories track the emissions from binaries. Gravitational wave detectors record the space-time tremors from merging pairs. Together, these observations form a mosaic of information that reveals not just the properties of individual objects, but also the broader story of how matter behaves at the highest densities. Each detection adds another point to the map of this hidden population, another step toward understanding how stars end their lives and what remains afterward. In the immensity of the Milky Way, neutron stars are both common and elusive. They are born in explosions, yet persist in silence. They are invisible to the eye but detectable across the spectrum of invisible light. They are small enough to fit within a city yet weigh more than the sun. Their presence ties together the life cycles of stars, the structure of galaxies, and the chemistry of planets. The universe is filled with these remnants, each one a frozen record of a single instant when a massive star succumbed to gravity and was reborn as one of nature's most extreme creations. Their quiet persistence forms an unseen backbone of the galaxy, a vast congregation of stellar ghosts holding their secrets behind a crust of impossible density, waiting for the rare moments when their energy or movement betrays their existence to the instruments of distant observers. When a newborn neutron star rotates rapidly and possesses a strong magnetic field, it becomes a pulsar, one of the most extraordinary natural beacons in the universe. These objects emit beams of electromagnetic radiation that sweep through space like cosmic lighthouses. Each pulse marks a complete rotation, and the intervals between them are astonishingly regular. This rhythmic flashing, detectable across radio X-ray and gamma-ray wavelengths, is the signature of an object both stable and extreme. The first pulsar was discovered in 1967 by radio astronomers who detected a repeating signal arriving every 1 1/3 seconds. It was so precise that at first they considered it might be artificial. Only later did they understand it as the heartbeat of a rotating neutron star. Since then, thousands more have been found, each with its own period, intensity, and magnetic geometry. The mechanism behind a pulsar's light is rooted in the interaction between rotation and magnetism. The star's magnetic axis is typically tilted relative to its rotational axis. As the star spins, charged particles trapped in the magnetic field are accelerated along the field lines, emitting radiation in tight focused beams. These beams can span a wide range of frequencies from long wavelength radio waves to high-energy gamma rays depending on the star's age and magnetic strength. When one of the beams crosses Earth's line of sight, telescopes detect a pulse of radiation. The regularity of these pulses is extraordinary. Some pulsars are more precise in timing than the best atomic clocks their rotation, slowing only slightly over centuries as they lose energy. Pulsars are often categorized by their rotation rate and magnetic field strength. Young pulsars formed in recent supernovae typically spin several times per second and have powerful magnetic fields that drive strong radiation and particle winds. Over time, as they lose rotational energy, their spin slows and their emissions weaken. Yet another group known as millisecond pulsars rotates hundreds of times per second. These are ancient neutron stars that have been spun up again through accretion of matter from a companion star. The process transfers angular momentum, reawakening the pulsar and producing a stable high-frequency signal that can persist for billions of years. The stability of these pulses allows astronomers to use them as natural laboratories. By timing their signals with extreme precision, scientists can measure minute effects predicted by general relativity, such as the warping of space-time near massive objects. Binary pulsar systems where two neutron stars orbit each other provide some of the strongest evidence for gravitational wave emission. As the pair loses energy through these waves, their orbits gradually shrink in a pattern exactly matching Einstein's predictions. These observations confirm the existence of gravitational radiation long before detectors could measure it directly. The power emitted by a pulsar is enormous. A typical young pulsar converts its rotational energy into electromagnetic radiation and particle outflows at a rate exceeding the Sun's total energy output by many orders of magnitude. Much of this energy emerges as a relativistic wind, a stream of electrons and positrons spiraling outward along magnetic field lines. When this wind interacts with surrounding material, it creates glowing nebulae such as the Crab Nebula, where high-energy particles collide with magnetic fields and emit brilliant synchrotron radiation visible across the spectrum. The pulsar sits at the center, its rotation driving a continuous flow of energy that sustains the nebula's glow long after the supernova itself has faded. Inside the pulsar, the immense magnetic field governs nearly every process. The field originates in the movement of charged particles within the star's crust and core, amplified during the collapse from the progenitor star. As the neutron star spins, the magnetic field sweeps through space, inducing electric fields that accelerate particles to near-light speeds. These particles, constrained by the magnetic geometry, produce coherent radio emission through complex plasma processes that are still not completely understood. Above the magnetic poles, gaps in the magnetosphere allow bursts of high-energy radiation to escape, forming the characteristic beams that define the pulsar's pulse profile. As pulsars age, their magnetic fields decay, and their rotation slows. Eventually, the emission mechanism becomes too weak to sustain detectable radiation, and the pulsar crosses what astronomers call the death line, becoming radio silent. The neutron star remains, but without sufficient energy to power its beams. Some of these objects may later be revived through accretion in binary systems, spinning up once more into millisecond pulsars. Others fade permanently into darkness, continuing their slow rotation unseen. This progression from youth to silence is part of the natural evolution of neutron stars and reflects the gradual loss of energy from rotation into radiation and heat. The study of pulsars has extended beyond astrophysics into broader cosmic applications. Networks of millisecond pulsars across the sky are now used as a galactic-scale gravitational wave detector. By monitoring the precise timing of their pulses, astronomers can detect minute distortions in space-time caused by passing gravitational waves from distant supermassive black hole mergers. The entire galaxy becomes an instrument with pulsars serving as its synchronized oscillators. The precision required for this work is extraordinary. Timing variations of only a few hundred nanoseconds can signal events occurring billions of light-years away. Beyond their scientific importance, pulsars embody the concept of order emerging from catastrophe. They are the remains of stellar collapse, yet their rotations and emissions display perfect regularity. Their pulses are cosmic metronomes marking the passage of time with unmatched precision. Some spin down so predictably that astronomers can forecast their slowing decades in advance. Others exhibit glitches, sudden, tiny increases in spin rate thought to result from interactions between the superfluid interior and the crust, offering rare glimpses into the star's inner structure. Each pulse, each glitch, and each long-term variation tells part of the story of how dense matter behaves under the most extreme conditions. The night sky is dotted with these unseen clocks, their signals arriving faint and steady through the noise of cosmic radio waves. Some pulsars emit primarily in radio wavelengths, others in X-rays or gamma rays depending on their energy output and magnetic alignment. Together they represent a continuum of evolutionary stages from newly formed neutron stars still surrounded by supernova debris to ancient millisecond pulsars stabilized by companions. To the human observer they are silent, but to instruments they speak in precise rhythmic tones that carry across space for millions of years. The rhythm of a pulsar is a kind of echo of the universe's own heartbeat, a repetition born from collapse, endurance, and balance. Each rotation is a testament to the conservation of angular momentum, each beam a reminder of the connection between magnetism and motion. Across the cosmos, thousands of these steady lights continue to flash long after their parent stars have vanished. They transform destruction into continuity, chaos into order, and silence into a steady pattern of light that endures for ages. Among the family of neutron stars, a small and extraordinary subset stands apart. These are the magnetars objects so intensely magnetic that they redefine the limits of physical strength in the known universe. A typical neutron star already possesses a magnetic field trillions of times stronger than that of Earth, but a magnetar exceeds even this reaching field, strengths up to a quadrillion times greater. Such an environment bends atomic structure itself, distorting the quantum vacuum around it and altering the behavior of matter and light. Magnetars are rare, only a few dozen confirmed in the Milky Way, yet they command immense attention because of their unpredictable and sometimes violent behavior. Where ordinary pulsars rotate steadily and fade quietly, magnetars are restless. They twist, fracture, and erupt, releasing bursts of X-rays and gamma rays powerful enough to outshine entire galaxies for brief moments. A magnetar begins its life like any neutron star born in the collapse of a massive star's core. The difference lies in the conditions at formation. If the collapsing core rotates extremely rapidly on the order of milliseconds, and if convection within it is strong, a dynamo effect may amplify the magnetic field to extreme levels. The combination of rapid rotation and turbulence acts as a cosmic generator, winding up the magnetic field lines and locking an enormous amount of energy within the star's interior. Within seconds, the newly formed magnetar carries more magnetic energy than all the stars in its galaxy combined. Over time, this field begins to decay, and that decay becomes the source of its distinctive outbursts. Magnetars reveal themselves through erratic flares. Some produce soft gamma repeaters, short, intense bursts of high-energy radiation, lasting fractions of a second. Others emit anomalous X-ray pulsations, their surfaces glowing with the heat generated by internal magnetic stress. The most powerful events, called giant flares, are among the most energetic explosions ever recorded outside of supernovae. In one such event observed in 2004, a magnetar located 50,000 light-years away released a pulse of gamma rays so intense that it briefly altered Earth's ionosphere. The origin of these flares lies in the crust of the star, where magnetic tension accumulates over time. As the magnetic field twists and shifts, the rigid crust cracks, releasing a sudden flood of energy. These starquakes are analogous to earthquakes, but on scales that defy human experience, liberating in a single instant as much energy as the sun emits in hundreds of thousands of years. The internal structure of a magnetar remains similar to that of other neutron stars, with a dense core of neutrons surrounded by a solid crust and a thin atmosphere. What sets it apart is how the magnetic field permeates every layer from the outer crust to the deep core. The field influences the movement of particles, the shape of the star, and even the behavior of the vacuum surrounding it. Light cannot travel in straight lines near a magnetar. Photons split or change polarization as they interact with the magnetic field. These quantum effects, predicted by theory and now observed through polarization measurements, make magnetars laboratories for studying physics beyond the reach of Earth's instruments. Rotation plays a key role in a magnetar's evolution. Most rotate slowly compared to ordinary pulsars, completing one turn every few seconds. Their strong magnetic fields extract rotational energy, rapidly breaking them within tens of thousands of years, an instant in astronomical terms. As they slow their fields, decay, releasing enormous amounts of heat and radiation. The combination of decaying magnetism and crustal fractures produces the bursts, flares, and persistent X-ray emission that define their character. Even after the most violent eruptions, magnetars often return to a quieter phase, radiating steadily as they cool. Over time, the surface temperature drops, the bursts grow infrequent, and the object transitions toward a more typical neutron star state. Observations across the electromagnetic spectrum have revealed that magnetars are not uniform. Some display both pulsar-like radio emission and magnetar-like flaring, blurring the distinction between categories. This suggests a continuum of behavior where the same physical principles operate at different intensities. The discovery of magnetars that emit radio pulses, for instance, challenges earlier assumptions that their magnetic fields were too strong to allow coherent radio emission. It appears that the boundaries between pulsars, magnetars, and other neutron star types are not sharp but fluid, governed by magnetic evolution and internal dynamics. The energy released during a magnetar flare has far-reaching consequences. The outburst drives powerful winds of charged particles into surrounding space, shaping the local interstellar environment. In binary systems, a flare can strip material from a companion star or disturb the orbital configuration. The radiation from giant flares may also serve as a source for some of the mysterious fast radio bursts, millisecond flashes of radio waves detected from distant galaxies. While their origins remain uncertain, the energies involved in magnetar activity are consistent with the scale of these phenomena. If magnetars are indeed responsible for some of these bursts, they link the small-scale physics of dense matter to the largest observable transients in the universe. Within the magnetar's crust, stress builds as magnetic field lines twist beneath the surface. The outer layers are only about a kilometer thick, but they are composed of matter so dense that a single cubic centimeter would outweigh a mountain. When the stress exceeds the breaking point, the crust fractures, producing vibrations that ring through the star like a bell. These oscillations have been detected as subtle modulations in X-ray light during giant flares, providing a glimpse into the star's internal structure. The way these vibrations fade reveals the strength and configuration of the magnetic field deep within, allowing scientists to infer details that cannot be measured directly. Despite their violence, magnetars are transient phenomena on cosmic timescales. Their active lifetimes last only tens of thousands of years before the magnetic field decays and the star cools into quiescence. What remains is a faint, slowly rotating neutron star indistinguishable from its quieter relatives. Yet during their brief periods of activity, they profoundly influence their surroundings, injecting energy radiation and heavy particles into the interstellar medium. In this way, magnetars contribute to the galaxy's broader ecology, seeding space with the energy that drives the evolution of nearby gas clouds and perhaps even triggering future star formation. The existence of magnetars underscores the universe's capacity to push physical laws to their limits. They are natural experiments in magnetism and density, revealing how matter behaves when compressed beyond atomic structure and threaded with unimaginable magnetic strength. Each flare and burst adds to a growing record of the ways in which gravity, rotation, and magnetism interact in their most extreme forms. Though they occupy only a tiny fraction of the galaxy, their influence is vast, extending across disciplines from nuclear physics to cosmology. They remind observers that even in the aftermath of destruction, the universe continues to create new expressions of energy and structure. The magnetar's brilliance is fleeting, but its echoes travel across space, carrying information about the boundaries of matter itself. When astronomers look at neutron stars through X-ray and optical telescopes, what they see is not the star itself, but the faint hard light emitted from its surface and thin atmosphere. The atmosphere of a neutron star is unlike any other found in the universe. It is only a few centimeters thick, yet within that layer the density and pressure are so extreme that ordinary atoms cannot exist as they do elsewhere. The gravitational field at the surface is hundreds of billions of times stronger than Earth's, meaning that any particle of gas is held tightly against the crust. Light emitted upward from this surface is bent by gravity, allowing observers to see more than half of the star at once. In this environment, the usual concepts of up and down, solid and gas become blurred. What appears as a glowing sphere is a crust of crystalline matter wrapped in an atmosphere that behaves more like plasma than air. The surface temperature of a young neutron star can reach over 1,000,000 degrees, producing radiation mainly in X-rays. Over time, as the star cools, this emission shifts towards softer X-rays and ultraviolet light. Observations of these spectra allow scientists to measure surface temperatures infer compositions and model the cooling behavior that reveals the inner structure. The thin atmosphere plays a critical role in shaping the light that escapes. If composed primarily of hydrogen or helium, the atmosphere affects how photons scatter and polarize. If instead it consists of heavier elements such as carbon or iron, the absorption lines shift, producing distinct signatures that telescopes like NICA and XMM Newton can detect. The nature of this layer depends on the star's history, whether it has accreted material from a companion or remained isolated since its formation. Beneath this atmosphere lies the solid crust a few kilometers thick, formed of atomic nuclei arranged in a crystalline lattice. The gravitational pressure squeezes atoms so tightly that electrons are forced into a degenerate gas, free to move through the lattice like currents in a metal. This outer crust is electrically conductive and supports the enormous magnetic fields threading the star. As the neutron star cools, the crust becomes rigid, capable of storing immense stresses that can later be released in sudden starquakes, producing brief X-ray outbursts. In magnetars, such crustal shifts are often the triggers for their explosive flares. Even in quieter neutron stars, these subtle movements can alter rotation rates, slightly producing the timing glitches observed in many pulsars. The surface of a neutron star is not smooth in the conventional sense. The magnetic field funnels particles toward the poles, heating them, and creating bright hot spots that rotate in and out of view. These regions, often only a few kilometers across, dominate the star's X-ray output, and produce the pulsating signals detected by telescopes. The rest of the surface may remain cooler, glowing faintly in comparison. This temperature variation provides information about magnetic field geometry, thermal conduction within the crust and the star's rotation. As light leaves the surface, gravitational redshift shifts its energy downward, meaning the observed radiation carries the imprint of both temperature and gravitational strength. Measuring these shifts helps constrain the star's mass and radius, two key quantities that define the equation of state for dense matter. The surface gravity of a neutron star is so intense that it shapes the behavior of all matter that approaches it. An object falling from a height of 1 meter would strike the surface at nearly half the speed of light. The impact energy is so great that in falling material vaporizes instantly, merging into the plasma atmosphere. The escape velocity from the surface exceeds 100,000 kilometers per second, meaning even light struggles to climb out. Because of this, photons leaving the surface are significantly delayed and redshifted, giving observers a distorted but informative view of the star. The strong gravity also ensures that any irregularities on the surface remain frozen in place. Mountains, if they can be called, that would rise only a few millimeters before being crushed by weight. Observations of isolated neutron stars have revealed subtle variations in surface emission that hint at complex magnetic and thermal structures. In some cases, the X-ray light curves suggest that the surface is covered with a patchwork of regions at different temperatures, possibly corresponding to magnetic domains beneath the crust. These patterns evolve over time as the star cools and its magnetic field decays, providing a slow-motion record of internal processes otherwise hidden from view. By studying the changes in brightness and spectrum, astronomers can trace the flow of heat from the core to the surface, learning how dense matter conducts energy under extreme conditions. The atmospheric composition also affects how radiation escapes. In a hydrogen atmosphere, photons scatter more freely, softening the emitted spectrum. In a heavy element atmosphere, absorption edges appear, producing sharper features that can be used as diagnostic tools. The detection of such features from certain neutron stars has allowed scientists to estimate gravitational redshift, directly offering one of the few methods to measure compactness, a ratio of mass to radius that reveals how close the object is to collapsing into a black hole. These observations tie together surface physics, nuclear structure, and relativity in a single measurable framework. For accreting neutron stars, where material from a companion star continuously rains down onto the surface, the atmosphere is in constant flux. The impact of infalling gas heats localized regions to tens of millions of degrees, producing thermonuclear bursts that briefly outshine the entire system. These bursts occur when the accumulated hydrogen and helium ignite under extreme pressure, releasing energy in a runaway fusion reaction. The resulting flash illuminates the star's surface, revealing information about its size, gravity, and energy transport. Each burst lasts only seconds, yet during that time the surface becomes a dynamic laboratory of nuclear and radiative processes. Despite the violence of these conditions, neutron star surfaces are remarkably stable. Over thousands of years, cooling proceeds predictably, guided by the balance between heat escaping from the core and energy generated by crustal reactions. Eventually, the surface temperature falls below 100,000 degrees, and the star becomes too faint for current instruments to detect. Yet even then, the structure remains intact. The lattice of neutron-rich nuclei continues to hold, the magnetic field persists, though weakened, and the thin atmosphere still clings tightly bound by gravity that no known force can overcome. When viewed as part of the larger cosmic cycle, the surfaces and atmospheres of neutron stars serve as boundaries between two realms, the visible and the invisible, the familiar and the incomprehensible. They are the outermost expression of matter that has been transformed by collapse yet still radiates light. Every photon that escapes carries the signature of conditions unattainable anywhere else. Through them, astronomers glimpse not only the temperature and structure of these objects, but also hints of the forces operating deep within. The light from a neutron star's surface is in essence the quiet echo of its violent birth, a fading glow that continues to whisper of density, gravity, and time long after the explosion has passed. Beneath the thin atmosphere and incandescent surface of a neutron star lies a layer unlike anything else in nature, the crust. This region, only about 1 or 2 kilometers thick, forms the solid outer shell of the star. It separates the visible surface from the strange, fluid interior, where ordinary atomic structure no longer exists. The crust is composed of exotic materials forged under pressures and densities that defy comprehension. It is both solid and flexible, crystalline and fluid-like, able to conduct electricity and heat with near-perfect efficiency. Here atomic nuclei are packed so tightly that they resemble a dense lattice of spheres immersed in a sea of electrons. The result is a rigid yet delicate balance between quantum mechanics and gravity. At the top of the crust, where density is lowest, the matter consists of nuclei similar to those found on Earth, though far more neutron-rich. The pressure is so immense that electrons are forced into high-energy states, moving freely throughout the lattice, and giving the crust a metallic conductivity billions of times greater than copper. As depth increases, the pressure rises dramatically, and the nuclei begin to absorb more neutrons from the surrounding environment. They grow heavier, distorted, and increasingly unstable. Around the midpoint of the crust, nuclei have become so neutron-rich that they verge on dissolving altogether, and free neutrons begin to drip out of the nuclei to form a continuous background fluid. This marks the transition between the outer and inner crust, a region known as the neutron drip point, where matter begins to lose its last trace of atomic individuality. In the inner crust, matter becomes a mixture of solid and liquid characteristics. The nuclei form complex shapes under the competing influences of nuclear attraction and Coulomb repulsion, creating structures sometimes described as nuclear pasta. Depending on the balance of forces, the matter may arrange itself into sheets, rods, or bubbles, each configuration minimizing energy under conditions of extreme density. These formations have evocative names: lasagna, spaghetti, gnocchi, borrowed from their geometrical resemblance, though their reality is profoundly alien. This nuclear pasta may be the strongest material in the universe, capable of withstanding enormous stress before deforming. It anchors the star's magnetic field, influences its thermal evolution, and plays a role in the starquakes that alter its rotation. The crust's mechanical properties are central to the behavior of neutron stars as a whole. When magnetic or rotational stresses build up, the crust can shift, suddenly releasing stored energy. Such events cause tiny changes in spin rate known as glitches, which astronomers detect as abrupt irregularities in pulsar timing. These glitches are among the most direct clues about the internal structure of neutron stars. They suggest that beneath the solid crust lies a superfluid interior that rotates slightly faster, periodically, transferring angular momentum to the crust when frictional forces overcome the pinning of vortices. The study of these timing anomalies allows researchers to probe the interface between solid and fluid matter, deep below the surface, an interface that cannot be reproduced in any laboratory on Earth. The crust also plays a vital role in regulating temperature. It conducts heat outward from the core, allowing the star to cool in a predictable pattern. Over thousands of years, this process establishes a stable temperature gradient between the hot interior and the cooler surface. Observations of cooling neutron stars, such as those in young supernova remnants, have confirmed this gradual decline, matching models that incorporate the thermal conductivity and composition of the crust. In some systems, accretion from a companion temporarily heats the crust to high temperatures, and when accretion stops, astronomers can watch it cool again, directly measuring its heat capacity. Such natural experiments provide invaluable data on how matter behaves at nuclear densities and under gravitational fields millions of times stronger than Earth's. Magnetic fields thread through the crust, anchored by electric currents that circulate within it. These fields evolve over time, slowly diffusing outward as the crust's conductivity changes. In magnetars, the decay of these fields injects heat into the crust, maintaining X-ray luminosity long after the star should have cooled. The interplay between magnetic decay and thermal evolution determines the lifetime of magnetar activity. Where fields are weaker, the crust remains more stable, and the neutron star cools quietly. This slow magnetic drift is a reminder that even in apparent stillness, these objects are in constant evolution, governed by the invisible movement of charge and heat through their dense outer shells. The density within the crust increases from about 10,000 times that of water at the top to roughly half the density of an atomic nucleus near the base. The transition to the core occurs gradually as the last vestiges of nuclear structure dissolve, and matter becomes a homogeneous mixture of neutrons, protons, and electrons. Yet this narrow layer, though tiny compared to the star's total size, determines much of its observable behavior. The crust controls how the star radiates heat, how it spins, how it interacts with magnetic fields, and how it responds to external forces such as accretion or tidal stress in binaries. It is the mediator between the visible universe and the unobservable depths within. The physics of the crust challenges conventional understanding of matter. Laboratory experiments can compress materials to perhaps a billionth of the pressure found here, leaving scientists reliant on theoretical models and indirect measurements. Observations of X-ray bursts, cooling curves, and rotational glitches serve as constraints on these models. Simulations using nuclear theory suggest that the elastic modulus of the crust, the measure of its stiffness, may exceed that of steel by 14 orders of magnitude. This makes it the hardest known substance, yet under magnetic strain, it can yield suddenly producing quakes that reverberate through the star. Such immense strength combined with fragility creates a paradoxical material both unyielding and restless. Despite its exotic nature, the crust is stable over cosmic timescales. As long as the neutron star remains intact, its crust preserves the record of its formation and thermal history. Some old neutron stars may carry crusts that have existed for billions of years, their composition slowly altered by accretion or diffusion, but still reflecting the state of the universe when they were born. In binary systems, repeated accretion cycles can replace the outer layers, burying older material and building new crust from fresh nuclear ashes produced by surface fusion. This renewal process connects the microphysics of nuclear reactions to the macroscopic evolution of the star, ensuring that even in apparent stasis, change continues at every level. The crust of a neutron star stands as a boundary in every sense between radiation and darkness, between stability and collapse, between matter as we know it and matter transformed. It supports mountains measured in millimeters, holds magnetic fields that can shape galaxies, and endures pressures that would crush atoms into uniform density. Beneath it lies the core, a realm even more extreme where neutrons move freely, and the distinction between solid and fluid disappears. But it is within this thin outer shell that much of the story of a neutron star's visible life unfolds. The light we see, the pulses we measure, and the quakes we record all originate in or pass through the crust. It is the silent foundation beneath every observable phenomenon, a fragile wall holding back the full weight of a collapsed star. Below the rigid crust of a neutron star, the nature of matter changes completely. The increasing pressure crushes nuclei out of existence, and the distinction between separate atoms dissolves. What lies beneath is the outer core, a dense fluid region, extending several kilometers toward the center of the star. Here neutrons flow freely among a smaller number of protons and electrons, all packed so tightly that quantum effects dominate their behavior. The densities reach values exceeding that of an atomic nucleus, roughly 100 trillion kilograms per cubic meter. The outer core is neither solid nor gas, but a superfluid and exotic state of matter where friction ceases to exist and particles move collectively as a single quantum entity. This layer is the largest and most massive part of the neutron star, containing the bulk of its weight and storing most of its rotational energy. The composition of the outer core has been the subject of intense study, because it determines the star's structure, cooling rate, and long-term evolution. Neutrons form the dominant component, but the fraction of protons and electrons, though small, plays a crucial role in maintaining electrical neutrality and influencing magnetic properties. The interactions between these particles are governed by the strong nuclear force which binds them together, even as gravity presses inward. The competition between these forces defines the equation of state for neutron star matter, a relationship between pressure and density that tells scientists how compressible the star is. Measuring this relationship indirectly through observations of mass and radius helps reveal what happens to matter under conditions that cannot be replicated anywhere else. In the outer core, temperatures may initially exceed 1 billion degrees, but fall rapidly as neutrinos carry energy away. As the star cools, the neutrons begin to pair up, forming what physicists call Cooper pairs, similar to the mechanism that produces superconductivity in metals at low temperatures. These paired neutrons condense into a superfluid that can flow without resistance. The protons likewise pair into a superconducting fluid that allows magnetic fields to thread through the core in thin quantized tubes known as fluxoids. The coexistence of these two quantum fluids, superfluid neutrons, and superconducting protons creates a dynamic interior where rotation and magnetism are intimately connected. The movement of these fluids drives the long-term evolution of the magnetic field and influences the star's spin-down rate. The superfluid nature of the outer core explains some of the most puzzling phenomena observed in pulsars. As the crust and core rotate at slightly different speeds, the superfluid interior can store angular momentum. When frictional forces suddenly transfer this momentum to the crust, the star's rotation rate jumps, producing the glitches seen in timing data. These events provide a rare observational window into the invisible dynamics beneath the crust. The regularity or irregularity of glitches across different pulsars suggests that the coupling between crust and core varies depending on magnetic field strength, temperature, and the distribution of vortices within the superfluid. Each vortex represents a tiny quantum of rotation, and billions of them fill the outer core, forming an array that maintains the star's angular momentum in perfect balance. Heat transport in the outer core is governed by the motion of these superfluid components and the scattering of neutrinos. As the star cools, neutrino emission becomes the dominant mechanism of energy loss, especially through processes known as the modified Urca and direct Urca reactions. In these interactions, neutrons convert into protons and electrons or vice versa, emitting neutrinos in the process. Whether the direct Urca process can occur depends on the proton fraction. If it exceeds a critical threshold, cooling becomes much faster. Observations of young neutron stars with unexpectedly low surface temperatures suggest that such rapid cooling may indeed occur, implying that their cores permit direct Urca reactions. These insights link astronomical data to the microphysics of dense nuclear matter, demonstrating how distant objects can test the laws of particle physics. The fluid interior also supports oscillations that ripple through the entire star. When the crust shifts or magnetic stresses build, vibrations propagate into the outer core, setting up standing waves that can be detected as variations in X-ray emission or timing noise. Some of these oscillations might couple to gravitational waves, producing faint space-time ripples that advanced detectors could one day measure. By modeling these vibrations, scientists can infer the viscosity, elasticity, and composition of the outer core, just as seismologists probe Earth's interior using earthquakes. The parallels are striking both planets, and neutron stars reveal their inner structure through how they respond to stress, though in a neutron star the energies involved are trillions of times greater. The transition from the crust to the outer core also marks a shift in chemical composition. The density at this boundary is so extreme that even light nuclei like carbon or oxygen cannot survive. Instead, matter transforms into a uniform mixture of nucleons. The balance between neutrons and protons depends on the conditions at birth and the long-term magnetic and thermal evolution. In some theoretical models, exotic particles such as hyperons, baryons containing strange quarks may begin to appear in the outer core, altering the equation of state and softening the matter's resistance to compression. The presence of such particles remains unconfirmed, but their possible existence adds depth to the mystery of what lies inside. Over millions of years, the outer core remains the engine that drives the neutron star's life. Its superfluid rotation maintains the star's spin long after external torques have faded. Its magnetic flux tubes slowly drift outward, shaping the decay of the magnetic field. Its heat flows upward through the crust, determining the cooling rate and surface temperature. Though invisible, the outer core's influence extends to nearly every observable property, from the precision of pulsar timing to the glow of cooling emission seen in X-rays. Even the gravitational waves produced in neutron star mergers carry signatures of how this dense fluid responds to tidal forces, offering another way to study its composition. The behavior of matter in the outer core challenges every physical theory developed under ordinary conditions. It is a regime where nuclear forces, quantum mechanics, and relativity all act together. A neutron star, in this sense, is a natural laboratory for testing the limits of physics, compressing mass energy and fundamental forces into a space no larger than a city. As technology advances, new observatories sensitive to gravitational waves, X-rays and neutrinos continue to refine our understanding of this hidden world. Each measurement of mass, radius, temperature, or magnetic field narrows the possibilities, gradually revealing the balance of forces that holds these stars together. The outer core is where the familiar world of atoms ends, and the realm of continuous nuclear matter begins. It is fluid yet rigid, stable yet dynamic, timeless yet changing. Within this layer, the legacy of a dead star becomes a new kind of order, a structure maintained not by chemical bonds, but by the interplay of quantum rules and cosmic gravity. It is here that the heartbeat of a neutron star truly resides, a deep rhythm of rotation, superfluid flow, and neutrino cooling that will continue long after the surface light has faded from view. Deeper still below the superfluid outer core lies the most enigmatic and inaccessible region of all the inner core of a neutron star. This is the final frontier of density, where the known forms of matter may dissolve into something new. The inner core extends only a few kilometers across, yet it contains most of the star's mass compressed into a state that pushes the limits of physical law. Here the density exceeds that of an atomic nucleus, and the distinction between individual particles blurs. Neutrons, protons, and electrons merge into a sea of subatomic components. The pressure is so intense that new species of particles unseen on Earth may emerge. At these densities, even the strongest known forces are challenged, and theorists are left to construct models guided only by mathematics, quantum theory, and the faint constraints provided by astronomical observation. At its simplest, the inner core could be viewed as a continuation of the outer core's superfluid mixture, but with increasing density, the behavior of matter changes in unpredictable ways. Some models suggest that exotic particles called hyperons baryons, containing strange quarks, form as neutrons are compressed and gain sufficient energy to transform. Their presence would change how matter responds to pressure, softening the equation of state and reducing the maximum possible mass of the neutron star. Other theories propose that with further compression, even these baryons dissolve into a soup of unconfined quarks, the fundamental constituents of all hadrons. This phase, often called quark matter or quark-gluon plasma, would represent a complete breakdown of ordinary nuclear structure. Within it, up-down and strange quarks might move freely, forming a new state known as strange matter. Whether such matter can exist stably within neutron stars remains uncertain, but it stands as one of the most intriguing possibilities in modern astrophysics. If quark matter forms in the inner core, the transition could have profound consequences. It would alter the mass-radius relationship of the star, affecting how much matter can be supported before collapsing into a black hole. It might also explain why some neutron stars appear to cluster around particular mass limits. Observations of heavy neutron stars, those exceeding 2 solar masses, imply that if exotic matter does exist, it must be strongly bound to resist further collapse. Otherwise, such stars could not survive. The delicate balance between gravity and internal pressure depends on the detailed microphysics of this region, and each new measurement of a massive neutron star helps narrow the possible equations of state that describe it. Within the inner core, quantum mechanics and relativity intersect in extraordinary ways. The neutrons, if they still exist as individual entities, form a superfluid in which the entire core behaves as a single quantum system. Rotational energy is stored in a lattice of vortices, each carrying a quantized amount of angular momentum. Meanwhile, superconducting protons allow magnetic fields to thread the region in quantized flux tubes. The interaction between these two networks, vortices and flux tubes, may determine how the star's rotation and magnetism evolve over time. Their slow movement, entanglement, and reconnection could release energy gradually or suddenly, contributing to the timing irregularities observed in pulsars. These microphysical processes, though invisible, have macroscopic effects that ripple outward to the star's surface and beyond. The pressures within the inner core are so great that even the fundamental symmetries of matter may shift. Some models predict that under these conditions, neutrons and protons lose their individuality, merging into a color superconducting phase of quark matter. In this state, quarks pair in ways analogous to electrons in a superconductor, allowing the matter to conduct color charge without resistance. This color superconducting phase could come in multiple forms, depending on how the quarks pair, some more symmetric, others broken into distinct color flavor arrangements. Each configuration would influence the star's mass cooling rate and magnetic behavior differently. While purely theoretical, these possibilities illustrate the extraordinary conditions inside neutron stars, where the laws of physics must be extended beyond their terrestrial limits. Because direct observation of the inner core is impossible, scientists rely on indirect evidence. The star's mass and radius, inferred from X-ray timing and gravitational wave signals, provide constraints on how compressible the interior must be. If the core is soft, easily compressed, the star will be smaller for a given mass. If stiff, it will be larger. Observations by NASA's NICER instrument have measured the radii of several neutron stars with unprecedented precision, allowing comparisons between models that include exotic matter and those that do not. Similarly, the detection of gravitational waves from neutron star mergers such as event G-7 revealed how these stars deform under tidal forces, offering additional clues to their internal structure. Each observation refines the range of possible conditions at the center, narrowing the window through which the truth of the inner core may one day emerge. Thermally, the inner core plays a dominant role in the star's long-term evolution. It acts as a vast heat reservoir, slowly releasing energy over millions of years. The rate at which it cools depends on what particles exist within it, and how efficiently they emit neutrinos. If exotic particles or quarks are present, new neutrino-emitting reactions become possible, accelerating cooling. Conversely, if the matter remains primarily nucleonic and superfluid, cooling proceeds more slowly. Observing surface temperatures of neutron stars at different ages helps distinguish between these scenarios. The coldest young neutron stars may already hint that exotic processes operate within their cores, allowing rapid energy loss through mechanisms unavailable to normal matter. The inner core also defines the ultimate fate of the star. As matter accretes in binary systems or during mergers, the additional mass increases central pressure. If the core's equation of state cannot support this pressure, collapse becomes inevitable. The star passes beyond the threshold of stability, its escape velocity surpassing the speed of light, and a black hole forms. The transition from neutron star to black hole marks the limit of matter's resistance to gravity. Understanding where this boundary lies, whether at 2, 3 or more solar masses, depends entirely on the physics of the inner core. Thus, even though this region is unseen, it sets the fundamental scale of compact objects across the universe. Within this compressed world, space and time themselves behave differently. General relativity predicts that near the center of a neutron star, the curvature of space-time is extreme though still finite. Light emitted from these depths cannot escape directly. Only the integrated effects of gravity and pressure determine what observers see. The entire structure is maintained by the delicate equilibrium between inward gravity and outward quantum pressure, a balance that persists for millions or even billions of years. In this sense, the inner core is not merely the heart of the neutron star, it is the point where physics pushed to its breaking point still holds together. What truly lies beyond this boundary remains uncertain. It could be that the transition from nuclear matter to quark matter happens smoothly, blending one phase into the next. Or it could occur suddenly, forming a distinct inner core of quark matter surrounded by a mantle of neutrons. Some theorists even speculate about more exotic entities such as boson condensates or phases with entirely new symmetries. For now, these ideas remain theoretical, but as observations of neutron stars grow more precise, they will test which of these possibilities nature has chosen. The inner core thus stands as both a challenge and a promise, a region hidden from view, yet central to our understanding of the universe's most extreme states of matter. At the center of every neutron star, unseen but fundamental, lies a relationship that dictates everything about its existence, the equation of state. This equation defines how matter behaves when squeezed by gravity into densities beyond those found in atomic nuclei. It links pressure, density, and temperature into a single framework that determines how the star holds itself together. From the equation of state, one can infer the star's radius for a given mass, the speed of sound within its core, the maximum weight it can support before collapsing into a black hole, and the way it deforms under external forces such as tides or rotation. Yet despite its importance, the true form of this equation remains one of astrophysics' most elusive mysteries. The extreme conditions within neutron stars cannot be recreated on Earth, and even the most advanced particle accelerators fall short of reaching comparable densities. As a result, scientists must deduce this relationship indirectly, combining theoretical models of nuclear physics with astronomical observation. In simple terms, the equation of state describes how compressible matter is. A soft equation of state means that matter yields easily to pressure, producing smaller, more compact stars for a given mass. A stiff equation of state implies strong resistance to compression, resulting in larger stars that can support more mass before collapsing. The difference between these scenarios can amount to kilometers in radius and entire solar masses' instability limits. Determining which description matches reality requires measuring neutron stars with extraordinary precision, observing their masses, radii, and tidal deformabilities through electromagnetic and gravitational signals. Every observation acts as a point on a curve that scientists attempt to reconstruct from afar using theory to fill the gaps between what can be seen and what must be inferred. At densities near the nuclear saturation point, about 2.8 times 10 to the 17 kilograms per cubic meter, laboratory experiments offer partial guidance. Nuclei in particle collisions and nuclear structure studies help constrain how neutrons and protons interact under pressure. But neutron star cores reach densities several times higher, where these constraints no longer apply and where exotic states of matter may form. The strong nuclear force described by quantum chromodynamics governs this regime, yet it is nearly impossible to calculate precisely due to its nonlinear nature. Theoretical models use approximations, each producing different predictions for how matter behaves. Some include hyperons or meson condensates. Others introduce quark deconfinement or color superconductivity. Each modification changes the stiffness of the equation of state, and consequently the predicted properties of neutron stars. Observations of neutron stars with masses around 2 solar masses have provided critical clues. If the equation of state were too soft, meaning the matter compresses too easily, such massive stars could not exist without collapsing into black holes. Their presence, therefore, rules out many theoretical models that predict too little internal pressure at high densities. Conversely, measurements of radii near 12 kilometers suggest that the equation of state cannot be excessively stiff either, or stars would be larger than observed. These twin constraints narrow the possibilities to a range of moderate stiffness, balancing compressibility with structural integrity. Each new measurement refines this window, gradually tightening the limits around the true physical description of dense matter. Gravitational wave astronomy has brought a new dimension to this search. When 2 neutron stars spiral toward each other and merge, their mutual gravity deforms their shapes, slightly producing tidal effects that imprint subtle signatures on the emitted gravitational waves. The pattern and amplitude of these waves depend on how easily the stars deform again, a direct reflection of the equation of state. The first observed merger, GISA 70817, allowed scientists to measure this tidal deformability for the first time. The data indicated that neutron stars are relatively compact, ruling out the most extreme stiff equations of state, and confirming that matter becomes significantly compressible at high density. Further detections continue to refine these estimates, transforming gravitational wave signals into tools for probing matter at nuclear densities. X-ray timing observations add another layer of evidence. NASA's NICA instrument, mounted on the International Space Station, measures the light curves from rotating neutron stars with hotspots on their surfaces. As the star spins, the gravitational bending of light and the Doppler effect alter the apparent brightness, allowing researchers to deduce the mass and radius simultaneously. These measurements have already constrained the possible range of equations of state, showing consistency between independent methods. Gravitational waves, X-rays, and radio timing, all converging on a coherent picture of moderately stiff matter. This convergence represents one of the great successes of modern astrophysics: multiple observation techniques, spanning different energies and messengers aligning to reveal the properties of an object that cannot be seen directly. The equation of state also governs the dynamics of neutron stars in motion. During mergers, it determines how much matter is ejected and how much remains bound. A stiffer equation of state tends to produce larger remnants that resist immediate collapse, while a softer one results in prompt black hole formation. The ejector rich in neutrons powers the kilonova glow that follows, producing heavy elements through rapid neutron capture. Thus, the physics of the inner core connects directly to the chemical evolution of galaxies, linking subatomic forces to the cosmic abundance of gold and platinum. Even the cooling behavior of isolated neutron stars depends on this equation, as it dictates the available reactions that produce neutrinos and conduct heat. In theory, the equation of state can be expressed as a simple relationship between pressure and density, but in practice it encompasses a vast array of microscopic processes. Quantum degeneracy, nuclear repulsion, pairing correlations, and particle creation all contribute. At lower densities near the crust, the equation is dominated by the stiffness of neutron-rich nuclei. Deeper inside by the interactions between neutrons, protons, and potentially quarks. The transition between these regimes may be smooth or abrupt, possibly involving phase changes analogous to those between liquid and gas. If such a transition occurs, it might create observable signatures such as discontinuities in the mass-radius curve or specific frequencies in gravitational wave spectra from mergers. Detecting these signatures would confirm that new phases of matter exist within neutron stars. The challenge lies in unifying all these elements into a single consistent model that matches observations across scales. Researchers use Bayesian statistical methods to combine data from different sources, treating each observation as a constraint on the underlying physical parameters. The resulting probability distributions reveal not a single equation of state, but a family of possibilities weighted by likelihood. With each new detection, the range narrows. The ultimate goal is to derive a universal equation valid for all neutron stars from the lightest pulsars to the most massive remnants approaching collapse. In the broader context of physics, the neutron star equation of state bridges the microscopic and the cosmic. It connects quantum chromodynamics, which governs quarks and gluons, to general relativity, which governs gravity and space-time. Few other systems unite these forces so directly. The success or failure of theoretical models in matching neutron star data serves as a test for our understanding of fundamental interactions. In this sense, every observation of a pulsar, every gravitational wave detected, and every X-ray spectrum analyzed contributes to one grand experiment conducted by the universe itself. Though the exact form of the equation remains uncertain, its influence pervades everything about neutron stars. It defines their birth, their stability, their evolution, and their death. It determines the boundary between star and black hole, the rhythm of pulsars, and the chemistry of galaxies. In seeking to describe it, scientists are not merely studying distant celestial bodies, but tracing the ultimate behavior of matter, the way the universe holds itself together under its own gravity. The quest for the true equation of state is therefore more than an astrophysical problem. It is a search for the limits of physical law written in the dense, unseen hearts of stars that no longer shine. To understand objects so dense and distant that no light can escape from their cores, astronomers must rely on indirect evidence, subtle signals imprinted in radiation timing and gravitational waves. Measuring a neutron star is not like measuring an ordinary star. Its entire visible surface is smaller than a city, its light bent and redshifted by gravity, and its behavior governed by physics that cannot be reproduced on Earth. Yet from these faint traces, scientists have learned to extract extraordinary precision. Every pulse spectrum and gravitational ripple carries information about the star's structure, composition, and evolution. The challenge lies in decoding those signals into physical quantities such as mass, radius, temperature, and magnetic field strength, all without ever seeing the object itself. The most fundamental property of any neutron star is its mass. In binary systems, where a neutron star orbits another star or another neutron star mass can be determined through the motion of the pair. Using precise timing of radio pulses, astronomers measure orbital periods, Doppler shifts, and relativistic effects like the precession of periastron. These data allow them to apply the same gravitational laws that govern planets and stars, but extended into the regime of relativistic compactness. The first such system, a pair of neutron stars discovered in the 1970s, provided not only the first accurate mass measurement, but also the first indirect evidence for gravitational waves. As the two stars orbited each other, their period shortened exactly as predicted by Einstein's theory, matching the energy expected to be carried away by gravitational radiation. Mass measurements have since expanded to hundreds of systems, revealing a surprisingly narrow range for typical neutron stars around 1.5 times the mass of the Sun, but with notable exceptions. A few extraordinary examples exceed two solar masses, setting firm lower limits on the stiffness of the equation of state. Each discovery pushes the known boundary of matter's ability to resist collapse. If future observations confirm neutron stars significantly heavier than this, theories of dense matter will need to accommodate pressures higher than currently modelled, possibly ruling out entire categories of exotic particles in the core. Thus, even a single mass measurement can reshape our understanding of the universe's most extreme physics. Determining radius is more difficult. The small size and intense gravity of neutron stars make direct imaging impossible, but several techniques allow indirect inference. X-ray telescopes such as NICER measure light curves from rotating neutron stars that possess hotspots on their surfaces. As the star spins, these spots move in and out of view, and gravitational lensing bends the light so that parts of the far side remain visible. By modelling the brightness variations and spectral shape, scientists can infer how much the light is distorted, an effect that depends on the star's compactness or the ratio of mass to radius. From these data, the radius can be derived with remarkable precision. Results so far indicate values between 11 and 13 kilometers, consistent with a moderately stiff equation of state. Temperature provides another window into the invisible interior. A young neutron star radiates heat from its surface as it cools after the supernova explosion. Measuring the thermal spectrum in X-rays reveals surface temperatures of millions of degrees, which gradually decline over centuries and millennia. By comparing observations at different ages, astronomers construct cooling curves that trace how efficiently the star loses energy. The rate of cooling depends on processes in the core, especially neutrino emission. If cooling is faster than expected, it implies exotic particles or direct Urca reactions are active. If slower, it suggests strong superfluidity that suppresses neutrino production. Thus, surface temperature becomes an indirect probe of deep unseen physics. Magnetic field strength is inferred from timing and spectral analysis. The spin down of a pulsar, the gradual slowing of its rotation, reveals how much energy it loses through magnetic radiation. From the rate of change of its spin period, one can estimate the dipole field strength, which typically ranges from 1 trillion to 1 quadrillion times Earth's. In magnetaires, additional clues come from X-ray bursts and polarization of emitted light, both shaped by the immense magnetic environment. These measurements allow scientists to map the star's electromagnetic behavior across its lifetime, tracking how fields decay and interact with crustal stresses. Together, timing and spectroscopy transform magnetism from an invisible property into a measurable dynamic force. Gravitational waves provide perhaps the most revolutionary method of all. When two neutron stars orbit each other closely, their gravitational dance generates ripples that propagate across space-time. The shape of the waveform encodes information about the masses, spins, and internal structures of the merging stars. By comparing observed signals with theoretical templates, scientists extract the so-called tidal deformability, how much each star is stretched by its companion's gravity. This property depends directly on the stiffness of the equation of state, linking macroscopic observation to microscopic physics. The first detection of such a merger in 2017 transformed neutron star research, offering direct measurement of their compactness and demonstrating that dense matter resists deformation more than expected, but not infinitely so. Subsequent events have refined these values, and future detectors will improve sensitivity, allowing individual components of the waveform to reveal internal oscillations and possible phase transitions in the core. Even isolated neutron stars can yield precise measurements. The timing of pulsars has reached such accuracy that some are used as galactic clocks. Variations as small as a few hundred nanoseconds can be detected, allowing researchers to study not only the stars themselves, but also gravitational effects along the path of their signals. Arrays of these pulsars form what is called a pulsar timing array, a network spanning the sky that detects low-frequency gravitational waves from merging supermassive black holes in distant galaxies. The consistency of these pulsars confirms their rotational stability and offers new tools for testing general relativity on cosmic scales. Each pulse from a neutron star thus serves not only as a heartbeat of a single remnant, but also as a signal from a precision instrument woven into the fabric of the universe. To connect all these diverse data, astronomers combine electromagnetic and gravitational observations into a field called multi-messenger astronomy. This approach allows cross-verification. X-rays probe surface conditions, radio timing measures spin, and magnetism and gravitational waves test the bulk structure. When all three types of data point to the same physical properties, confidence in theoretical models grows. The 2017 merger was a milestone in this regard. It produced gravitational waves, gamma-ray bursts, and optical kilonova light, all from the same event. This combination confirmed that neutron star collisions create heavy elements and provided simultaneous checks on mass radius and energy output. Each new detection strengthens this emerging discipline, where every type of messenger adds a new dimension to understanding the unseen. Despite their remoteness, neutron stars are among the most precisely measured objects in the cosmos. Their small size and extreme regularity make them ideal, natural laboratories for physics that can be tested nowhere else. They allow measurements of fundamental constants, limits on gravitational theories, and constraints on particle interactions. Instruments now being developed, including more sensitive gravitational wave observatories and high-resolution X-ray polarimeters, will extend these capabilities further, turning once speculative ideas into measurable phenomena. The precision of these efforts is staggering. A pulse arriving a few microseconds earlier or later can reveal the presence of a planet, a companion, or a shift in the star's interior. In a universe filled with vast and diffuse structures, neutron stars stand out as concentrated repositories of truth. They condense not only matter, but also information. Every bit of data extracted from them, whether a pulse, a spectral line, or a gravitational chirp, is a coded message from a regime where physics is stretched to its limits. The act of measuring them is an act of interpretation, reading faint whispers from a place where time slows and matter strains against collapse. Through careful observation and relentless refinement, humanity continues to translate those whispers into understanding, transforming the unseen into the known. When two neutron stars form a binary system, their mutual gravity binds them in an intricate and deadly dance. Each revolves around the other, emitting gravitational radiation that carries away energy and angular momentum. Over millions or billions of years, this emission causes the pair to spiral gradually inward, drawing them ever closer, until in their final moments they merge in one of the most powerful events in the universe. These collisions mark the culmination of stellar death, and the rebirth of elements releasing gravitational waves, light and matter, in a spectacle that links the smallest scales of nuclear physics with the larger scales of cosmology. Long predicted by theory and confirmed by observation, neutron star mergers have become one of the most valuable laboratories for understanding both dense matter and general relativity. The approach begins quietly. Two massive stars born as a binary live their main sequence lives side by side, burning through their fuel and eventually exploding as supernovae in turn. If both survive as neutron stars, the remnants remain gravitationally bound. Each orbit distorts space-time around it, radiating gravitational waves whose amplitude grows as their separation shrinks. For most of their existence, this radiation is too faint to detect, but over eons it drains energy, steadily shrinking the orbit. When the stars are only a few hundred kilometers apart, their velocities reach a significant fraction of the speed of light, and the emitted gravitational waves enter the frequency range detectable by instruments on Earth. In these last few seconds, the inspiral accelerates, producing a rising chirp signal that encodes the mass spin and internal structure of each star. As the stars draw near, tidal forces deform them slightly. Their shapes elongate toward one another, and this deformation affects the gravitational wave signal in measurable ways. The magnitude of the distortion depends on the stiffness of the equation of state, the same property that defines how compressible matter is inside neutron stars. Stiffer matter resists deformation, producing smaller tidal effects and a cleaner chirp, while softer matter yields more, altering the phase of the wave. Thus, by analyzing the waveform, scientists can infer the internal physics of the colliding stars without ever seeing them directly. When the first such merger, GWF 7 was detected in 2017, it provided a direct measure of this tidal deformability, confirming that neutron stars are compact yet not infinitely rigid. It also verified that gravitational waves travel at the speed of light as predicted by general relativity. At the moment of contact, the two neutron stars compress and twist around each other, merging into a single hypermassive object. The density briefly exceeds that of any stable configuration, and the remnant may collapse into a black hole within milliseconds. The gravitational wave emission peaks sharply, followed by a rapid cutoff as the event horizon forms. But before collapse, the remnant radiates intense magnetic and thermal energy. Shock waves tear through the merging cores, ejecting neutron-rich material into space. This ejector, moving at 1/10 the speed of light, expands and undergoes rapid neutron capture reactions, producing heavy elements such as gold, platinum, and uranium. The radioactive decay of these nuclei powers a transient glow called a kilonova, whose color and brightness evolve over days. When GDR 70817V was followed by a kilonova observed across the electromagnetic spectrum, it confirmed that such mergers are a primary source of heavy elements in the universe, a direct link between the death of stars and the chemistry of planets. The gravitational wave data combined with the light from the kilonova revealed an astonishing level of detail. The total mass of the merging system was about 2.5 times that of the Sun, with each star contributing roughly equal parts. The aftermath produced a short gamma-ray burst, one of the brightest explosions known, arising from jets launched along the poles of the remnant. These jets, powered by magnetic fields, wound up during the merger travel near the speed of light, releasing high-energy photons as they collide with surrounding material. The sequence of signals, gravitational waves first, then gamma rays followed by optical and infrared light, painted a coherent narrative of a single event observed through multiple messengers. It was the first time in history that humanity witnessed the complete life cycle of a cosmic cataclysm in real time. Since then, additional mergers have been detected, each with unique properties. Some result in immediate black hole formation, others leave behind unstable remnants that survive briefly before collapsing. The difference depends on total mass rotation rate and the equation of state. Simulations show that if the remnant's mass is below a critical threshold, rapid rotation can temporarily support it against gravity, forming a hypermassive neutron star. This object emits gravitational waves of high frequency as it oscillates, violently radiating energy until centrifugal support fails and collapse ensues. Detecting these post-merger oscillations remains challenging because they occur at frequencies beyond current detector sensitivity, but future instruments are being designed to capture them. Such signals would provide a direct probe of the inner core's behavior during compression beyond normal limits, a fleeting glimpse into matter on the brink of turning into a black hole. Mergers are also key to understanding population statistics. By measuring how often they occur across cosmic time, astronomers estimate how many neutron star binaries exist and how their formation depends on star formation rates. Each detection improves estimates of the rate of heavy element production in galaxies, confirming that a significant fraction of gold and other R-process elements originate from these events. The gravitational wave background produced by countless past mergers may even fill the universe with a faint hum detectable through precise pulsar timing arrays. These arrays, using the steady rhythm of millisecond pulsars, can sense tiny distortions in space-time over years, complementing the higher frequency signals observed by terrestrial detectors. The energetic consequences of neutron star mergers extend far beyond the immediate vicinity. The ejected material enriches the interstellar medium, spreading heavy elements that later become incorporated into new stars and planets. Over billions of years, this process seeds galaxies with the building blocks of life and technology. Meanwhile, the gravitational waves carry information about the expansion of the universe itself. Because their amplitude diminishes predictably with distance, they can serve as standard sirens, allowing astronomers to measure cosmic distances directly without relying on intermediate calibrations. The first such measurement from GW 087 yielded an independent estimate of the Hubble constant linking local astrophysical events to cosmological scales. In merging systems that include a black hole and a neutron star, the dynamics change further. If the black hole is small enough or spins rapidly, tidal forces can tear apart the neutron star before swallowing it. This process releases gravitational waves with distinct features and ejects neutron-rich material similar to that from neutron star pairs. Observations of such events test the boundaries between compact object types, confirming how matter behaves in the strongest gravitational fields known. Each merger, whether between two neutron stars or a mixed pair, adds another point of comparison, sharpening models of extreme matter and validating Einstein's theory in regimes never before tested. Ultimately, neutron star mergers are both destructive and creative. They mark the violent end of two stellar remnants, but also the beginning of new matter, new light, and new insights into the universe. The gravitational waves they emit vibrate through space-time as pure geometry untouched by dust or distance. The light they release carries the fingerprints of freshly minted elements. Together they tell a story of unity between physics and astronomy, between microcosm and macrocosm. In every sense, these collisions are cosmic experiments, compressing nature's laws into moments of extraordinary clarity. The data gathered from them already span the disciplines of nuclear physics, high-energy astrophysics, and cosmology. And though each event lasts only seconds, its echoes continue for years, teaching humanity how the universe evolves and how even death among the stars can give rise to something entirely new. In the depths of a neutron star merger, the universe forges its heaviest elements. Gold, platinum, uranium, and dozens of others that cannot be created inside ordinary stars are born in moments of unimaginable violence. For decades, astronomers searched for the primary site of this alchemy. Supernovae were once considered the main source, but their calculated yields fell short. Only with the detection of the kilonova that followed the first observed neutron star merger did the puzzle finally begin to resolve. The light from that event, fading from blue to red over several days, carried the spectral signatures of newly synthesized heavy nuclei. It confirmed that neutron star collisions are major factories of the universe's rarest materials. These elements, essential to planets and civilizations, originate in the destruction of stars that once shone billions of years ago. The creation of heavy elements in such mergers follows a process known as rapid neutron capture, or the R process. It requires an environment rich in free neutrons and sufficiently energetic to fuse them into atomic nuclei faster than they can decay. When two neutron stars collide, enormous quantities of neutron-dense matter are expelled into space. As this material expands and cools, it undergoes nuclear reactions that assemble increasingly heavier nuclei. Each step adds a neutron, and as unstable isotopes beta decay into protons, the atomic number increases, building elements along the periodic table all the way to uranium and thorium. The sequence takes only seconds, but determines much of the universe's chemical diversity. Without such rapid neutron capture, the periodic table would end near iron, the last element formed through normal stellar fusion. Everything beyond precious metals, radioactive isotopes, even the iodine in the human body owes its existence to this process. The ejected material from a merger is complex. Some originates from tidal tails pulled out of the stars as they orbit, while other portions are expelled from the collision shock or from winds driven by the hot accretion disk surrounding the remnant. Each component experiences different conditions of density, temperature, and electron fraction, leading to a diverse mix of elements. The outermost layers, less neutron-rich, produce lighter process elements like strontium and silver. The deeper, denser layers generate gold, platinum, and actinides. When the kilonova light fades, its evolving color reveals which elements dominate. Early blue emission corresponds to lower opacity material rich in lighter elements. Later red emission signals heavier lanthanides and actinides, whose complex atomic structures trap light more efficiently. By modeling this transition, astronomers can estimate how much of each element was created. A single merger may produce several Earth masses of gold and tens of Earth masses of platinum scattered into interstellar space to become part of future worlds. The confirmation of this process unified astrophysics, nuclear physics, and cosmology. Observations of ancient stars in the Milky Way's halo show abundances of heavy elements consistent with early R process enrichment. Some of these stars, nearly as old as the galaxy itself, contain ratios of europium, barium, and other elements that match those produced in modern kilonova models. This suggests that neutron star mergers occurred even in the early universe, enriching the first generations of stars long before the Sun was born. Chemical evolution models trace these events through cosmic history, showing how successive generations of mergers gradually increased the metallicity of galaxies. Every speck of heavy metal, every atom of gold in a wedding ring or microchip has likely passed through this cycle of stellar death and rebirth. The link between neutron stars and the periodic table also highlights the unity of physical laws. The same nuclear forces that hold protons and neutrons together in atomic nuclei govern the structure of neutron stars themselves. In one context, they stabilize the matter inside atoms. In another, they determine how matter behaves when compressed to nuclear density. When these forces are momentarily released during a merger, they drive nuclear synthesis on a cosmic scale. This connection transforms the understanding of astrophysics from a study of distant stars into a direct exploration of the same interactions that shape the material world. The boundary between the laboratory and the universe dissolves. The periodic table becomes a record of cosmic events. The kilonova of 2017 provided the first direct evidence of R-process production, but since then additional events have reinforced the conclusion. The brightness, color evolution and spectra of each observed kilonova reveal consistent patterns. Some mergers appear richer in heavy elements, while others produce mostly lighter ones, suggesting that variations in neutron star masses, spins, and magnetic fields can alter nucleosynthesis outcomes. Simulations show that slower ejecta, which remain hot, longer favour heavier element formation, while faster ejecta freeze out earlier, limiting the chain of neutron captures. These nuances imply that not all mergers contribute equally to cosmic chemical enrichment. Rather, a range of outcomes shapes the diversity of elemental abundances across galaxies. Even after the initial explosion, the remnant disk and winds continue to synthesize elements. If a black hole forms quickly, it swallows most of the material, limiting further production. But if a hypermassive neutron star persists for even a fraction of a second, its intense magnetic fields and neutrino flux can drive additional outflows. These outflows are less neutron-rich but still contribute to the total yield. Observations of long-lived afterglows help constrain how long such remnants survive, and by extension, how much material escapes their gravity. Each piece of evidence refines the understanding of how much of the universe's heavy element budget originates from these cosmic forges. On Earth, isotopic ratios preserved in meteorites and ancient rocks reflect this history. The abundance of radioactive elements such as uranium and thorium, whose long half-lives power planetary interiors, points to contributions from multiple past mergers in the region of the Milky Way where the solar system formed. The heat that drives Earth's geological activity and the metals that fill its crust are therefore the long-term legacy of collisions that occurred billions of years before our planet existed. Even the gold and platinum mined for human use are relics of these ancient cosmic furnaces. In this sense, every civilization is materially connected to the lives and deaths of neutron stars. Beyond their chemical significance, these mergers serve as precise tests of relativity and nuclear physics. The gravitational wave signals from each event reveal how matter behaves at the point of collapse, while the electromagnetic emission records the subsequent nuclear reactions. The combination of these two messengers provides one of the most complete views ever achieved of any astrophysical process. The agreement between theoretical models and observation in these cases confirms that the same laws governing subatomic particles also govern the behavior of entire stars. Yet mysteries remain, such as the precise distribution of R-process yields across the universe and the relative contributions from other possible sources like rare types of supernovae. The answers lie in the detailed modelling of future kilonovae and the continued detection of mergers by next-generation observatories. In the grand scheme of cosmic evolution, the creation of heavy elements marks the transition from a universe of simplicity to one of complexity. The first stars forged only hydrogen, helium, and trace lithium. It took billions of years of stellar birth and death to enrich galaxies with carbon and oxygen, and the cataclysmic collisions of neutron stars to provide the final ingredients, those elements that enable planetary cores, biological processes, and advanced technology. The gleam of metal in human hands, the energy flowing from nuclear reactions deep in planets, the very possibility of chemistry itself, all trace back to these fleeting explosions. Every atom heavier than iron carries within it a record of pressure gravity, and time imprinted during a few seconds of cosmic transformation. Through mergers and colonovae, the universe continually recycles its material, ensuring that the debris of one generation of stars becomes the foundation for the next. The heavy elements that condense into planets, flow through oceans and form the structure of life, are at their origin remnants of collapsed stars torn apart in gravity's most extreme experiments. To observe these events is to witness creation at its most fundamental level, the forging of matter itself. And in that forging lies a connection between the distant cosmos and the smallest detail of existence, between the merging of neutron stars and the gold dust of human civilization. Even after decades of observation and theory, neutron stars still conceal more than they reveal. Each discovery opens new questions, and every measurement narrows the boundaries of uncertainty without closing them entirely. These objects sit at the edge of what physics can presently describe. They are dense enough that gravity bends light and time, yet not so dense as to disappear into black holes. They contain matter compressed to the brink of quantum breakdown, yet they persist in stable form for millions of years. They link the macroscopic scale of galaxies to the microscopic scale of quarks. But the ultimate nature of their interiors, their magnetic origins, and their long-term evolution remain partly hidden, leaving scientists to piece together clues scattered across space and time. The most enduring mystery lies at the center. Despite progress in measuring mass radius and tidal deformability, no observation can yet reveal the exact composition of the inner core. The possibility of quark matter hyperons or entirely unknown phases remains open. Theoretical models predict transitions that could occur suddenly or smoothly, as density increases but direct confirmation is lacking. Gravitational wave observations from future mergers may detect faint oscillations that betray the presence of these transitions. The way a neutron star deforms rings or collapses under stress might carry the fingerprint of its inner state. Until then, physicists continue to refine their equations of state, comparing predictions with every new data point, searching for consistency among theories that span many orders of magnitude in scale. Another mystery concerns magnetism. The origin and evolution of magnetic fields in neutron stars are only partly understood. The amplification during collapse can account for immense strengths, but why some stars become magnetars while others remain ordinary pulsars is unclear. Perhaps small differences in rotation or convection during formation determine whether a magnetic dynamo ignites. Perhaps external conditions such as surrounding material or binary interaction play a role. Over time, these magnetic fields decay, rearranging within the crust and core, but the exact mechanisms remain uncertain. Observations of bursts, flares, and glitches provide glimpses of internal activity, yet the full picture of magnetic evolution, how it begins, how it changes, and how it ends, remains elusive. Even the thermal life of a neutron star poses questions. Cooling curves match general patterns, but display anomalies that suggest hidden processes. Some stars cool more rapidly than expected, implying efficient neutrino emission, while others retain heat for longer. The difference may depend on superfluid pairing gaps, exotic particles, or crustal composition, but no single explanation fits all cases. Similarly, the connection between surface hotspots and interior heating remains complex. Magnetic reconnection, crustal motion, or residual accretion may all contribute, but disentangling these effects requires data of extraordinary precision. Each deviation from theoretical prediction is a signpost pointing toward deeper physics not yet fully grasped. Fast radio bursts, millisecond flashes of radio energy arriving from distant galaxies add a modern layer of mystery. Some repeat, others do not, and their origins remain debated. The energies involved suggest compact, highly magnetized sources. Magnetars are leading candidates supported by detections of similar bursts from a known galactic magnetar in 2020. Yet the diversity of observed bursts implies more than one origin, perhaps including young neutron stars' binary interactions or collapse events. These signals travel across billions of light-years, allowing the intergalactic medium to shape them, but within each lies a signature of its source's physics. Understanding them may reveal how magnetars evolve, how their fields reconnect, or even how energy is released from the quantum vacuum around them. The population of neutron stars in the Milky Way also presents unsolved puzzles. Only a tiny fraction are visible as pulsars or X-ray sources, leaving the vast majority hidden. Many may drift silently through space undetectable except through their gravitational influence. Some may reside in binaries too faint or distant to observe. Others may be remnants of early generations of stars, their rotation slowed and fields decayed to invisibility. Surveys with next-generation telescopes aim to uncover these missing members through subtle signals such as microlensing or gravitational waves from unseen pairs. Mapping their distribution will clarify how many have been born since the galaxy's formation, and how their properties evolve with time. In the realm of extreme physics, neutron stars also test the boundaries of general relativity. Current observations confirm Einstein's theory even under intense gravity, but future precision may uncover deviations. Some alternative theories predict slight differences in how gravitational waves propagate or how space-time curves near a compact object. Detecting such variations would revolutionize physics, pointing toward a deeper unification of gravity with quantum mechanics. The timing of pulsars orbiting black holes or other neutron stars could eventually reveal these subtle effects, turning celestial systems into laboratories for testing the foundations of space-time itself. Beyond science, neutron stars provoke philosophical questions about matter and persistence. They are the densest objects that can exist without vanishing behind an event horizon, embodying a delicate equilibrium between creation and collapse. Their light, steady and rhythmic, continues long after their progenitor stars have died. Their collisions produce the materials that shape worlds and life. In their existence, destruction and renewal are inseparable. They compress the universe's history into a single object, the ashes of fusion, the triumph of gravity and the seeds of future creation. Yet they remain indifferent, drifting through space, spinning down over eons, cooling, until only faint whispers of radiation remain. Future instruments promise to bring these mysteries closer to resolution. Next-generation gravitational wave detectors will capture higher frequency signals, revealing details of post-merger oscillations. Space-based observatories will measure X-ray polarization, exposing how magnetic fields twist light near the surface. Improved timing arrays will detect subtle variations caused by passing gravitational waves or unseen companions. Together, these tools will extend observation beyond the current limits, transforming speculation into measurable reality. With each new dataset, the unknown retreats slightly, though perhaps never completely. Still, the fundamental enigma of neutron stars, the balance between known and unknown, may endure as part of their allure. They remind humanity that even as technology expands perception, there remain frontiers beyond reach. They are relics of processes that occurred long before life on Earth began, yet they continue to evolve on timescales that far exceed human existence. Their quiet persistence offers perspective. The universe operates according to laws that are both comprehensible and endlessly deep. Neutron stars embody those laws at their limits where gravity and quantum mechanics meet, not in theory, but in reality. When we look at them through telescopes tuned to invisible light through the vibrations of space-time or through the elements they have sown across the cosmos, we are witnessing matter at its most honest expression. Stripped of complexity, devoid of fusion or flame, they represent pure balance between force and resistance. In their rotation, in their silence, and in their mystery, neutron stars continue to challenge and guide our understanding of nature. They are both destination and beginning and answer to the question of what happens when gravity wins, and a question about what lies beyond that victory. The search to understand them is far from over, and perhaps it never will be. For as long as they spin in the darkness, the mysteries they hold will mirror the universe itself, immense, patient, and still unfinished.